Hello everyone, my name is Anant Sakharkar. This is my presentation for the final term project FFT Hardware Accelerator. I have used Quartus 2 software, Neos 2 software build tools and Altera DE1 board for my demonstration. The goal of the project is to demonstrate how hardware accelerators can offload specific tasks from the processor and can run faster if entirely executed in software. Before I begin, I would like to thank Professor Chang Chu for the guidance and San Jose State University Electrical Engineering Department for allowing me to present this demonstration. Let's begin with the demonstration now. You first have to open the Quartus 2 software. Before I begin, let me clarify there are two parts for this project. The first one is software approach and hardware approach. The goal, as I have said earlier, the goal is to demonstrate the differences between the clock cycles executed for both of them. So let me first start with the software approach. I'll open the already executed program. So that is FIR QSys. So in the first step, you have to define your Cyclone 2 processor name. So I have seen it, you can see it from the DE1 board. The second step towards the project is run the QSys system. So when you open the QSys system, you'll see all the blocks in terms of modules. So you have to drag and drop them into the project window, connect them together, and once you hit the generate, it will create an entire system for you. Since I've already created the QSys system, I'll open the same. So this system creates this sort of environment in QSys. So you can see a clock which is already generated and set to 50 megahertz, a Neos 2 processor which can be added from here, on-chip memory on-chip memory set to 8 kilobytes, JTAG UART port for serial connection with the DE1 board, and performance counter for measuring the clock cycles taken for the FFT calculation. All the clocks and reset have been connected properly from clock for all the gates. Clock in reset is provided only to the Neos 2 processor. Since on-chip memory is connected to the processor and gives instructions to the processor, it's connected to the processor. No other components are connected to the instruction master. Data master is connected to all the blocks from processor to all the peripherals. There is an interrupt request from JTAG UART to the processor. Once you build all this, once you put all these models in this window, you have to go to the system, assign the base addresses, and there will be multiple errors present. The second step would be to set the go to the Neos 2 processor. The reset vectors and exception vectors, you have to select it from none to on-chip memory. Just to show you, I have used Neos 2 economical processor for my implementation. So once you hit generate, system would generate a .qsys file which can be used for the further process. Since I've already generated the QSys system and the generation takes more time, I would skip this step. The next step, once you go in this, you will see no files under the files section. So you have to go to the files, add remove files to the project. Obviously there won't be any files present over here. You'll have to go to the software folder where I have stored the project. You'll see the QSys system which is just been generated. You have to go to the project named folder. You'll see a synthesis folder, and you have to select a .qip file which has all the files of all the generated Verilog files combined together into one single file. You have to select this file and to open it. Since I've already opened, I would cancel this step. So after doing this, once you have included this file, it will appear over here. You can see all the files included. Then second step, you have to do the assignment. You have to go to the assignment editor. You have to do the assignments as specified over here, since those are the two important pins which will be used. One clock is set to the pin L1 and second clock is to the 3.3 volt LVTTL value, and both of them are assigned as clock and IO standard. Once you do this, you'll see a tick mark appearing. Initially there would be a question mark, so once the system recognizes it's a proper generated value, you'll see a tick mark over here that indicates the status is okay. Once this two steps are processed, you hit the compile button. The compilation is done in following steps. That is, first the analysis and synthesis is done, then the filter, the place and route, then the programming files which are generated. One of those files is .sol, that is SRAM object file, which we need to burn on the DE1 board. Then the time-based timing analysis, which we actually have skipped for this project. The EDA netlist writer step is proceeding next, and the entire progress can be seen from this beautiful progress bar. Since the generation is taking a lot of time, I would explain in brief about the systems, the problems have occurred and the version of Quadus I've used. I was trying with very many different versions of Quadus and Neo software build tools, and I figured out the version 11.1, that is version 11 and Service Pack 1, which found out to be more stable than any other versions. Of course, version 9.0 Service Pack 9.0 is more stable too, but since it's an older version, it supports very less functionalities, not QSys. It has SOPC builder. So I'm using version 11.1 for this step. So as you can see, the compilation is almost finished right now. You can see there are no errors. Second step is to go to the programmer. You'll already see the .sf file which has been generated right now being appeared over here. You have to select the program and configure function and hit the start. Make sure you have already connected your DE1 board to the computer and it is set to the run mode instead of program. Now you have to go to the QSys. Pardon me. You have to go to the software build tools. You have to go create a specific special directory called software inside your actual project directory. Once you open it, you won't be seeing any project files over here since I've already generated the files. Those are appearing over here. Your first step would be go to the NEOS to application BSP file template. You have to select the SOPC file name over here. So once you select the .sopc info, the system would automatically recognize the CPU name for this. You have to give a project name for this project. Possibly the same project name appended with an underscore neos would be more elaborative. Then you have to give the project location. Once you do that, you have to select the templates. So Hello World and Hello World Small are two templates which we can use. I've used Hello World Small as it gives very small memory footprint. So once you do this, you have to hit the finish, and these two folders could appear over here. One of them would have a C file which would have only a print statement just to indicate that the board is connected to the computer. So since I've already generated the process, I've already completed the process. I'll walk you through the through my project file. So I have replaced my initial system generated C file with this file. So that has a declaration uh, of the performance counter base address. The performance counter base address could be found out from the system.h file over here, or you can go to the, for easier approach, you can go to the SOPC info, and once you open the .sopc info file in QSys editor, you can see the file, the start address over there. So I would go to the performance counter declaration, which is in system.h file. You can see the base address is set to 5000. So that's the reason I have used 5000 as a base address over here. Second step, I have defined two cases which were in the project. I'll be using first case for my demonstration. I have used all my code inside this performance counter declarations. So you have two declarations, one for start and one for the end. So between those two files, you have to keep your project. So that would measure the clock cycles taken. Once you do all this, you have to save the file, clean the project, and you first have to build the project, clean the project, and you have to run it as in your hardware. So since the code is already present inside the NEOS2, since the Altera D1 board, I'll have to refresh it. The way to refresh it is to click the BSP folder, go to NEOS, generate BSP. This would generate the BSP for this specific project. So it would show all the BSP files have been generated. Now you have to clean the project. Once the cleaning is successful, you have to go and run the project as NEOS2 hardware. Remember, once you do this step for the first time, you have to build the project first. So you can see the progress over here. The refreshing make files is in progress. You can also have a watch on the console window. So generation is successful right now. You can see the filter output as correct as it was expected, the -34 for the given set of inputs, and the computation was completed in 176783 clock cycles. I have noted these clock cycles just to compare them with the hardware approach. Once we do the comparison, we'll able to see the difference between the hardware and software approach. So this concludes my software approach presentation. I hope you have enjoyed it. Thank you. Hello everyone, my name is Anant Sakharkar, and this is my presentation for the final term project FFT Hardware Accelerator. I have used Quartus2 software, NEOS software build tools, and Altera DE1 board. The goal of this project is to demonstrate how hardware accelerators can offload a specific task from the processor and can run faster if entirely executed in software. Before I begin, I would like to thank Professor Chang Chu for the guidance and San Jose State University Electrical Engineering Department for allowing me to present this demonstration. This is the part 2 of the video where I would be showing the hardware portion of my project. So the entire goal of the project is to compare the clock cycles taken by the software only approach and the hardware approach and compare the best one. So let me start with my Quartus project. So this is my project which I have already opened. If not open, you have to go to File, New Project, Wizard, and create a project. Select the proper Cyclone chip. Go to the QSys. Open the QSys QSys file which I've already generated. Otherwise, you have to build file. QSys is the program in which you can drag and drop the system components, connect them together, and once you hit generate, it will generate a bit of Verilog HDL files towards the project which you are planning to perform. As you can see, once you open the QSys, you see the basic clock which is added. Apart from that, there won't be any components. I would add the components which I have generated earlier. So those before this thing is completed, I'll tell you the components which I've added. So those are NEOS processor, on-chip memory, JTAG UART, performance counter, and a custom component that is named as the FIR128. So just in the previous case, this NEOS 2 processor is connected to all these peripherals using the data master. On-chip memory is connected to NEOS 2 processor using instruction master, and the reset and exception vectors of NEOS 2 processor are set to that of on-chip memory. Clock and resets are connected properly, and instruction interrupt request is selected from JTAG UART to processor. Make sure you do the system assign base addresses step before you hit the generate. This would make a proper base address generation. Then second step is the one which I have mentioned just now. Go to the NEOS processor and select the reset and exception base vectors to be that of on-chip memory. Then you have to click generate. Since the generation takes a lot of time, I have already generated the file which is having an extension .qsys. Let me minimize this and go back to the Quartus project. So this is the Quartus project. After this step is finished, you won't be seeing any project file under this folder. You have to go to manually add and remove this file. Go to the project directory, go to the project name directory, go to synthesis. Here you have to select the .qrp file, which is the you can say the combination of all the Verilog files which the QSys tool has generated. Select this QRP file, hit open. This will appear here. Add it to the project. Hit OK. This file would appear over here. So as you can maximize, you can see all this Verilog files, all the files which are required are all added just in form of one file. Then second step is go to assignment, go to assignment editor, do all these two assignments. Since all the other assignments are not necessary, like that of the pin assignment, default pin assignments, that of LED, then switches, so those are all excluded. So I have defined two clock assignments, one set to pin L1 and other to 3.3 volt LVTTL. One of the location assignment and other for the IO standard assignments. Once you do that, you will see the status turn to OK. Hit compile. It will start compilation. Just to this step is to show that the already generated QRP file is in good shape, and that actually makes the compilation successful. So while the compilation is in progress, I will show you the NEOS SBT tool interface. So we'll simultaneously keep an eye on the project progress. Yeah, so now you go to NEOS SBT, you won't be seeing these two files present. So before you go to arrive at this screen, you have to select the workspace. The workspace by default should be under the project directory. You can create another separate directory, naming it as hardware, since this is a hardware approach. After that, go to the file, Alt-Shift-N, that is create a new NEOS 2 application from BSP template. So this would open this screen. Select the SOPC file that will be generated with this Quartus step. So this Quartus will basically generate the SOPC info file and SOF, all the necessary files required for the simulation. Go to the SOPC info, select the SOPC information file. In this case, from my previous generation, I have this SOPC info file. Once you click open, it will by default select the CPU name. You have to give project name to this project. You can give the same project name, or it would be better if you could give the project name appended with a QSys, just to appended with NEOS, just to make you aware that this is a NEOS project. Then you have to select the Hello World small template, as it gives very small memory footprint. After you all these steps, you have to hit finish. So once you will see two folders appearing over here, those two folders will have necessary files for the software implementation for the NEOS to process up. So as mentioned, the generation or the selection of this SOPC info file creates a NEOS QSys, makes you select NEOS to QSys 0 CPU, which I have generated in the SOPC. So you have to select the project name. So you have to select finish at this point, but I am selecting cancels as I have already generated the file. So while the file still the quarters compilation is in progress, the quarters compilation is progress, is about to finish. So let me shift our focus to the quarters right now. So there you see the full compilation was successful with no errors. You have to hit OK. Click the programmer, which would burn the recently generated SOF file to the DE1 board. Make sure you have selected USB Blaster 0 over here. Hit start, which would show the progress of this SOF file burning. Make sure it's 100% successful. Go to the NEOS to SBT. Make sure you have followed all the steps which I have told you right now. So as I've said earlier, there will be two files. One will have this .c file. Right now I've modified the .c file from the default just print statement to this entire FFT program. As you can see, I have assigned the base addresses for FIR as well as for the performance counter, even the inputs for the input and coefficients. Created the performance counter loop in which I have to add the FFT program. So once I've done this, I have to save this. After saving this, I have to build the project by clicking right click, build project. It would also clean the project, and then I have to run it as a NEOS 2 hardware. But since I have run this project earlier, I'll have to clean this project. So this can be done by going to the ._BSP folder, go to NEOS 2, generate BSP. What this would do is it would override the earlier generated files with the newer ones. So the BSP files which are required are replaced with are refreshed basically. So this step is complete now. Just to make sure I clean the project. So cleaning is successful, I believe. So now I can run it as NEOS 2 hardware. So you can so it's looking for valid launches right now. The NEOS to BST SBT is still in progress. As I've said earlier, the target connection is not refreshed. So because of the old generation, you have to refresh the connection. So it would show the JTAG UART connection opened over here. You can the download ALF file and start processor are already been selected. What we can do is you can select the ignore mismatch system ID and ignore mismatch system timestamp to remove any errors, forthcoming errors. Do run. So you can see the generating make file is in progress right now. You can keep an eye on the console to see the actual output. So there you go. So there is my project information. You can see the result is same as that of the software, except that the computation is completed in 22,683 cycles. If you remember, the earlier the software cycle, the cycles which have taken for the software approach were 176783 cycles. So the difference, the number of times this hardware approach takes is almost 7.79 is to 1. So that is 8 times is to 1. So you can see the hardware approach is 8 times faster than that of the software approach. So this concludes my presentation for the hardware approach. I hope you have enjoyed my presentation. Thank you so much.